But I'm hearing about casting.
The papers, I mean, yeah, the tests are something, but then the papers and the homework add up to something else too, and you want to do well on those.
I'll do okay. I'll do fine.
So then it's just doing. Then all you have to do is do well enough on the exams.
That's my concern. That is the exact concern. If they just do not so great on the exams, but then on the final you do well.
But then because they drop one exam, you're okay. Whoa.
Actually, if you look at this, homework and papers is already 35%.
Yeah.
If you get 35% on the exams, which is
you can get a D on the exams and still pass the class.
All right. It's not the goal.
Right.
You know, as long as they can do it. We have lofty aspirations.
There you go.
That's a little right of hope. Yes, I know, right? That's what we need to know.
All right. Come on, friend.
Oh, he's going to give us like
explain the paper to us.
Yeah. How do you want to approach this?
Let me just get everything going here.
Yeah.
Oh, how could you possibly be confused?
So we should make a ratio graph of the ice cube.
No.
It's a ratio graph.
Radiograph. Well, probably radiograph, right?
Start with the radio. What would a radiograph look like? Or a radiograph like an X-ray?
Like an X-ray.
All right.
What would it look like? I don't think they're going to let you put an ice cube tray on an X-ray and zap it in there, will they?
Probably not there, but at the hospital, we can do that.
It's very interesting to try it.
We did. At the VA hospital.
You zap some ice cubes?
Ice cube and water.
What did you see?
Well, the water, you can see nothing. There's no definition. Oh, I can pull it out.
Could you see anything with the ice?
Yeah. You can see the ice.
Can you explain why you can see those? Because water is ice, it's the same material, right?
No, it's not.
It is. Same chemical composition. If you melt ice, you get water. It's a crystal structure.
Yeah.
Why does that matter? Why does that matter?
Because you're removing the electrons. So you might be shifting the...
Well, see, that's what the whole second paper is about. Why does it matter that the ice is has a different density than the water?
So do you want to... He wants you to explain why.
Yeah.
What you're trying to explain is what he wants you to write about.
Yeah.
Yeah. Water, actually. Right, that's water. Water. In the cup. And the ice is more radiolucent. The ice is more radiolucent. Yeah, this picture is not even radiopaque. No, radiolucent.
Radiolucent means that the X-ray goes right through it.
Uh-huh.
What am I trying to do here?
That's the ice.
So yeah, get that picture of the ice. Explain why it has.
Can you use the image now and see the shape?
I'd love it.
Yeah.
That would be great.
No, look, it's right here.
With the water, it's
But
like you're just.
that's only one part of it. The whole thing is called differential absorption.
You know what you need. You know what you need to
And
really do.
density has an effect, but there are other things that have an effect.
More radiopaque. This is water.
The word is differential
I feel like you're
absorption.
seeing the cup though, not the
No,
water.
no.
Wouldn't have anything to do with scattering.
This inside is all water. I mean, all this is
So-
water.
In chapter,
Or the bottom of the cup.
it's in
Did you shoot it from the X-ray tube going down?
the chapter that has to do with
I feel like I'm gonna do a ski cube.
Yeah. Hey, that's a good.
it's in the chapter that has to do with X-ray interactions with matter.
Oh, okay.
That's where you'll find it, and you'll find it called differential absorption. And density is simply one thing. Differential absorption is what you're looking for. And you'll find it in the chapter on X-ray interactions with matter. And of course, since you're focusing on differential absorption, you don't have to worry about scattering. It's absorption, it's not scattering.
We'll have to go into the bonding.
Yeah. It's very straightforward when you see it. You'll go, whoa, that stuff's so easy.
That's good news. Like everything else, right?
Yeah.
So that,
It actually is. It is one of the easier parts of the whole thing once you get the feeling for it. You know, there's just a couple of things to deal with, and it's quite straightforward.
I get it.
and it says like what would this tray and water looks like in a graph. You were asking.
And an X-ray, right?
I mean, the X-ray, but we don't literally have to make a graph of the ice.
Graph, radiograph, another word for X-ray image.
I thought you were talking about like a graph.
No graph, no graph.
I feel like
An actual image.
everything should go graph.
But I missed a radiograph, X-ray image, old word for it.
Either the X-ray tray or like the cups, whatever you choose to use, you'd have to take it together. You'd have to take a picture of them empty first, so you know what that looks like, and then take a picture with it.
Okay, so you'll find most of the information
And from above.
in that chapter, and it's on X-ray interactions with matter. And again, the ice cube tray is just a starting point. You should be able to figure out what that is. You should be able to, without, just from your understanding of differential absorption, you should be able to explain why the picture of ice and water is what it is. And so hopefully you can tell me ahead of time before you take the picture of it what it looks like, and then just use that as a starting point to discuss differential absorption. If you start now, you can get it done. Any leftover questions from the exam? Everything? Well, we're not going to, I'll tell you what, I will put up some solutions, but I won't put them, I don't want to spend the time today to go through them. I should have got the solutions done, but I didn't. A couple of things we did want to, that might help with some of it. Where'd it go? Here's another, try this, see if this works. Ooh. It does work, kind of. Better picture of the X-ray tube. It's out of your textbook or a textbook. I don't know if it was shown in a textbook. Tube current exists between here and here. This being the filament, this whole thing itself being the cathode, that being the anode. The anode rotates, all that good stuff. Target, the X-ray window, the X-rays come out there. Electrons go flying across there, X-rays go out that way. Any real surprises there? Okay. Oops. Where did I put it? So I also found this picture in the book just for fun. There we go. So it's the same part of the tube, but just reminding you that the stator, here we have the rotator, the anode is connected to this thing. Here's your windings, and you can recognize that there would be coils of wire using inductance to make this whole thing rotate. You know what that's all about. So this is this. Just turn on the end view so that you can see it. Good picture. a sort of interesting picture in the book.
It's saying no textbook.
I'm not sure. It's in the last version of it. It probably is, because he doesn't change the pictures too much. The publishers have still not given me the new book. So here's another picture of your X-ray tube, and it's just talking about heat conduction. So this X-ray tube produces a whole lot of heat, because it's not a very efficient process getting X-rays. Remember, we've got this beam of electrons feeding that thing, and it's causing that to get very hot. It's like you got this little intense beam of particles hitting it. It causes that to get very hot. And there is some heat removal by convection. Here we have a fan rotating air. Remember, convection, you just simply move the hot air to where you want it, or get rid of it, blow it out the window, or whatever. Conduction, like you're heating something on a stove. And of course, the radiation. We remove some energy simply by radiating it away in the form of photons, some of which are electrons. So, in that picture, you could quickly identify the filament current and the tube current with absolute certainty. Okay, cool. Keep that picture in mind then. And let's take a look at tube current versus filament current. Now we have two scales, left and right. We have half wave and full wave, referring to a rectification. And you have a series of lines for the different voltages. Okay, the kVp, remember, is your accelerating voltage. It's that which makes the electrons go faster. Bigger kVp, faster electrons. Which current has to do with the electrons crossing from the cathode to the anode? Was that the filament current or the tube current? You knew it 30 seconds ago with absolute certainty. The tube current. Going from the cathode to the anode is the tube current. And that's what we have on the left and right sides. One of them is for half wave rectified, the other is full wave rectified. Part of our topic today is rectification. On the bottom we have our filament current. Filament current, that's the current that gets the filament hot and the filament boils off the electrons, and the electrons are then accelerated across the tube. Hence they're called the tube current. Okay, filament current of 4.6 amps at 100 kVp. Wave. What is your tube current? Read it off the graph. So we're 100 kVp, so you're looking along this line. We're going to said, what, 4.6? So we read up until you hit that line, rather. And then you want to read to the side that says full wave, which would be in that direction. What do you want to call that? Maybe 215, something like that. $2.15, and what are the units? Milliamps. Notice that even though you have a rather large filament current, that's in amps, you get a small tube current. There's not a direct, simple relationship between tube current and filament current. It's a complex relationship. You don't have a mathematical relationship between them. That's why we have to have these graphs. Yeah?
So the 2 on the side is just whether your rectifier is full wave or half wave?
Correct. And tube current versus KVP, this graph. Very important graph here. Come on. So on the horizontal axis, you see KVP. On the vertical axis, you see tube currents. And the different lines here now are your different filament currents. And the interesting behavior is that at the low KVP, you have a low tube current. Now, why would that be? Your tube voltage is very small. You're not really accelerating those electrons very much. As you increase the voltage, the electrons start accelerating, and your tube current increases. But only up to some point, and then it's a maximum. In the engineering world, when things hit a maximum like this, it's called a saturation. You dial it up as high as it'll go, and you just can't get any more out of it. We call it saturated. So this flat line refers to saturation.
So that's like the maximum amount of electrons?
It's the maximum amount of tube current, electrons, passing from cathode to anode that you can get with, in this case, a filament current of 4.6 amps. Dialing up the KVP will not increase your tube current. So the other sort of terminology that is kind of awkward here is, okay, we have emission limited and space charge limited. And you have to learn what those mean. Let's start with the emission limited. What's emitting? Pardon? Giving off. Emission. What's being emitted? What emission are we talking about? Actually, not the X-ray. That's why it's kind of deceptive. We're talking about the emission of electrons from the filament. So when you see this emission, it is the emission of electrons from the filament. And what this is saying is that basically every single electron that is emitted from the filament is just immediately whisked away and accelerated towards the target, you know. And if there were more, then how would you get more? We crank up the tube current to get more electrons being emitted. So then you can increase it, but you have to increase the filament current. So I think of this as sort of every single electron that comes off the filament is being used. On the other side, we have space charge limited. This is a little bit harder concept. Space charge sounds like something out of Star Wars. Does words do anything for you? No? Well, okay, skip the space charge and do the limited. Does that do anything for you? Limited means it's...
Cannot exceed a certain point.
Yeah, it's kind of, it's, how about the word inhibited? Does that do anything for you? Something is inhibited, it's not allowed to go. Right? So there's a charge in space. There's your cathode. And then right in front of your cathode, you have this filament. And the filament is emitting electrons. There's a cloud of electrons emitted from the filament. These are the ones that have all been emitted. And electrons. How do electrons feel about other electrons? They don't like them, yes, as long as you can be anthropomorphizing our little electrons. They don't like electrons. And in fact, the fact that these electrons are already emitted and they're kind of hanging around, they inhibit other electrons from coming off the filament. So these electrons that hang around the filament, this is what we call space charge. Now, why would electrons hang around the filament?
They're not accelerated.
Because they're not accelerated, or it takes a little bit of time for them to accelerate, or there's just a whole lot of them. So when the accelerating voltage is low kVp, you get a space charge buildup. A low kVp space charge buildup. Okay. The idea here, space charge limited. Or you might want to rephrase that as space charge inhibited. Or you might want to rephrase it as too many already emitted electrons hanging around inhibiting other electrons from being emitted. That's kind of a long sentence. Sure. Too many already emitted electrons hanging around inhibiting other electrons from being emitted. Sort of a longer version of what space charge is.
How?
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 How what?
How is it inhibited?
Well, the electrons here are negative, and because there's a cloud of negative charge here, the electrons are less inclined to actually leave the filament.
So to get rid of the space charge limit, you increase the kVp.
Yep, exactly that. If you increase the kVp, the electrons are whisked away, and you get rid of your space charge buildup, and hence the electrons can come off the filaments, and you get more X-rays. So the big deal here is that your tube current for a certain range is independent of kVp. Here's the sentence. Too many V's and independent there. Where is the tube current independent of kVp? And of course, the converse of that sentence Where does it depend on KVP, and where is it independent of KVP? And those two sentences refer to the two shaded regions there, but which one goes with which?
It's independent at the information limited.
So we have two sentences, we have two regions here, the light gray and dark gray. Which one is which?
Dependent is space charge limited.
Dependent is space charge limited, exactly. Yeah.
So at the saturation point, that's for a given current, that's the maximum amount of electrons we can give out. That's what it means.
So at the saturation point means that changing the KVP will not increase your tube current.
Okay. So does that mean that it's the maximum amount of emitted electrons?
Well, since we're talking of current here, it's actually a rate of electrons per second being emitted, but yes, that's what it means.
Okay.
You could interpret it that way. So that says, the way I think of it is every electron that's being emitted is being turned into tube current right away, and because all of them are being used, you don't get any more tube current by increasing the KVP. So let's just try one word problem here. With a tube current of 4.8 amps, Golden current, not tube current. Well, you've got a filament current of 4.8 amps, and if I change the tube current from 50 to 90 kVp, would I expect a change in tube current? So, question here is how would you answer it? You're looking at 4.8 amps. 50 kVp would go up to here. And it's in the space charge limited. And at 90 kVp you'd be over here. So yes, you'd have a change of, well, maybe 100 milliamps. So I would say the answer is yes. Because the 50 kVp is prior to the saturation point. Right. Questions? All right. So I want to talk a little bit about rectification. And I found this PowerPoint online. It's kind of fun to play with, so I put it up here for you to play with. What's the purpose of rectification? It fixes a problem. To rectify is to make right, right? It's kind of a fun little PowerPoint because it's got some animations in there. You've got your alternating voltage. It's not the best PowerPoint, but it's kind of fun. And of course, just looks like a heart attack on it, but it's not that bad. You kind of recognize what's going on, right? We got a high voltage transformer, some transformer, that's right here. And you could identify where the fundamental current and the feed current are. So you would recognize that the fundamental current must be somewhere in here. Here is your anode. And the X-rays are going off in that direction if I wanted to put them in there. And this strange thing is our rectifier. And this little symbol is the symbol for what's called a diode, which this diode is a strange word for an electric valve, electric one-way valve. It only lets electrons go one way. Rectification, the process by which alternating current is changed to pulsating direct current. Then you get to practice your French. Avec voyage. Okay. So here we have this. You're going to explain this thing? Because you had a whole section on inductance. What you see is a wire loop in a magnetic field, right? Mm-hmm. And the amount of magnetic field is changing as it passes through that wire loop. In this case, it's caused by rotating the wire loop instead of changing the magnetic field. And we get our AC generator. Then it makes alternating current. And you can kind of get the feel of what these arrows are doing. They're telling us that the electrons flow in the wire one way, and then they turn around and flow the other way. It's alternating current. ACM, that wasn't supposed to happen.